Momentum is a quantity that kind of represents mass in motion or objects in motion. And so momentum is simply the product of mass times velocity. Another way to think of it, we call it inertia in motion. So it's a moving object, it's mass in motion. Okay. This is a very simple equation, P equals mv. Unit-wise, right, momentum would be kilograms mass times velocity meters per second. And unlike force, where we had like newtons or some other sort of derived unit, that's it for momentum. There's no derived unit. It is simply kilograms times meters per second, and that's our unit for momentum. So momentum is kind of an inertia-like quantity. It's, a mass, it's inertia, and it's in motion. So it's kind of the combination of those two things. So what it represents on its own is a little bit abstract, but what we can do with it and how we can use it to analyze certain things, especially collisions, is very useful. One of the interesting things about momentum is that it was actually the original way that Newton wrote his second law, right? We're used to seeing it as F equals ma. Newton's original form of the second law was actually F equals delta P over T, which is a slightly different way of writing it. The delta P over T actually can be converted to a calculus thing. Since Newton was into his calculus, that's the real form of how he wrote it. But for us, delta P over T is very similar to how he wrote it. So let's take a look at that real quick. So F equals delta P over T. Well, delta P would be change in momentum, so change in mass times velocity over time. Well, that quantity, mass times velocity, mass isn't really going to change in any given situation. It's not just going to randomly gain or lose mass. But it will change velocity, so we can actually factor out the mass times a change in velocity over time. Well, focus on just this part of the equation for a second. What's a change in velocity over time? Well, a change in velocity over time is an acceleration. So we can see that that was kind of the original, kind of matches with Newton's second law, and this form up here, our momentum form, was actually Newton's original form of his second law. It also leads us to another kind of interesting thing. So if we take this equation, and we're going to rearrange it a little bit differently, this time I'm going to say force times time equals change in momentum. Now this quantity, force times time, has a special name, and that is impulse. So that quantity, force times time, which is equal to change in momentum, is called impulse. This is a really, really important thing when it comes to analyzing collisions. What that means is that for any given change in momentum, force times time has to equal that change in momentum. So a really good, quick application of this is, say, an airbag in a car. Well, in a car crash, you're going from some speed to zero, so your change in momentum is fixed. However, if you can make this time increase, so more time for that force to be applied, then what happens to force in order to keep the same value? If this increases, force must decrease. So that's kind of how an airbag works in the car. By allowing more time for that force to be applied, that change in momentum happens over a longer period of time, so your force is decreased. When we talk about the force in a collision, it's kind of important that we understand what we're talking about with this force here. This force here is actually the average force during a collision. The real graph of a force during a collision looks something like this, where we're going to have this nice little curve where kind of things are initially touching and then they reach a peak, and then as things slow down, they're not pushing as hard against each other anymore, and so they kind of slow down to a stop. Well, these are varying values for force, so we can't just like pick a value and throw it into the equation. But what we can realize is that if I took an average sort of thing, kind of cut this right down the middle, that this area under the curve, if I added this area, and that would be the same as adding these two little pieces here. So by taking an average force, we're kind of getting this area under the curve correct, regardless of how we do it. And force times time, this quantity impulse, when you're calculating it, is actually the area under the curve here. So by taking an average force, you're really being fairly accurate with it, even though our forces during a collision aren't exactly perfectly even the whole time. So here you have a tennis ball. being hit up to a speed of 58 meters per second. We want to know what the force is. And we have the mass, and we have the time. So we can use our impulse equation, force times time equals change in momentum. So force times time equals mv final minus mv initial, right? V final minus v initial would be our change in velocity, right? Always final minus initial for any kind of change. Well, the initial velocity of the ball is going to be 0 before it's hit. So that goes to 0. We're looking for force. We have our time here. So let's solve this for force. mv final over time. So force is going to equal my mass, 0.057 kilograms, times my velocity, well, it reaches a speed of 58 meters per second, divided by my time of 5 milliseconds. So that's going to be 5.0 times 10 to the negative 3 seconds for milliseconds. And then solving for force, we get that force was 661.2 newtons that was applied to the ball in order to get it to accelerate to 58 meters per second over those 5.0 milliseconds.